My research in the Hybrid Systems Lab under Professor Riccardo Sanfelice focuses on developing control algorithms for a wide variety of engineering applications and studying the resulting closed-loop stability properties. Example applications include motion planning for driverless cars, flight controllers for aircraft such as quadcopters, and rendezvous and docking controllers for spacecraft. In particular, we focus on the analysis of what are called hybrid dynamical systems, which are systems that exhibit both continuous time dynamics, called flows, and discrete time dynamics, called jumps. A canonical example of such a system is a bouncing ball, shown in Figure 1. As the ball travels through the air, its position and velocity change continuously with time. However, each time the ball impacts the ground, the direction of its velocity vector changes instantaneously, signifying a jump. I am interested in the topic of parameter estimation for hybrid systems. For example, in the bouncing ball problem, we may be interested in determining the mass or the elasticity of the ball based on measurements of the ball's position as it bounces. My recent research focuses on developing hybrid gradient descent algorithms for parameter estimation of hybrid systems. Gradient descent methods seek to determine a local minimum of a function by taking repeated steps in the direction of steepest descent. That is, given a function which can be visualized as a contoured surface, a gradient descent algorithm advances in the downhill direction of the surface until the lowest point is reached. We applied these methods to an electrical circuit called a DC to DC boost converter, shown in Figure 2. This circuit consists of a voltage source, an inductor, a capacitor, a diode, and a switch in connection with an output load. The purpose of the circuit is to provide a higher voltage at the output compared to the input by toggling the switch in a particular manner. Boost converters are a common component in the power systems of electric vehicles, where they are used to supply power from the regenerative braking system to multiple different components, each of which may have its own unique voltage requirements. Since the converter input voltage and load resistance vary as the car accelerates and brakes, it's important to estimate the values of these parameters in real time. We developed a hybrid parameter estimation algorithm which determines the input voltage and load resistance of the boost converter circuit. Notably, this algorithm provides finite time convergence of the parameter estimates, as opposed to more classical estimation schemes that converge only asymptotically, in other words, as time goes to infinity. This finite time convergence property is particularly useful for applications such as the boost converter that require online implementation, since the stability properties of a chosen control scheme typically only hold when the system parameters are known. We then took this parameter estimate and designed an adaptive uniting control algorithm for the boost converter. Uniting control schemes utilize a divide and conquer approach to control design by combining multiple distinct control algorithms to achieve the desired closed-loop stability properties. In our case, we combined two control schemes. The first provides global asymptotic stability of the set point, but produces arbitrarily fast toggling of the converter switch in steady state. The second is an industry-standard pulse width modulation control scheme that provides satisfactory performance, but only locally near the set point. The uniting controller selects between the two control algorithms based on the boost converter state in relation to two uniting control sets, shown in Figure 3. The global controller, with trajectories shown on the left in blue, is selected when the converter state is outside of the red ellipse, and the local controller, shown on the right in magenta, is selected when the converter state enters the green circle. As a result, the global controller is applied while far from the set point, and the local controller is applied when close to the set point. Example trajectories for the closed-loop boost converter system under parameter uncertainty are shown in Figure 4. On the left, we have the capacitor voltage and inductor current. On the right, we have the estimates of the input voltage and load resistance, each of which converge to the true values in finite time, followed by subsequent convergence of the capacitor voltage to the desired value. We provide formal proofs that guarantee global asymptotic stability of a neighborhood of a desired set point voltage for the closed-loop system, even under uncertainty in the boost converter input voltage and load resistance. This result represents a significant improvement over the stability properties of the current industry-standard pulse width modulation control scheme. Thank you all for your time.